All right, guys, we're ready for video 7. It's a continuation of the definite integral, and it's a use of that. We're going to use summative notation or sigma notation to write these definite integrals. So this is a general way it looks. This is something that you should be familiar with already. So this is our integral from a to b of our function dx. Remember, this is our function times the change in x. All right, so then our limit as n approaches infinity is basically this integral is just the sum of all those little rectangles, guys, right? So let's break it down. The little rectangles have your widths. Your width of the rectangle is delta x, and then your function is the various values you get when you plug in like the different heights, right? That's what you're doing here. So that's what this part is. And then again, it's the sum of all those rectangles. So how do we get these things? Well, our delta x is the width of our rectangle. So think about it. It would be the difference between a and b, and then divided into n sections. So in this case, we're letting n be infinitely many sections because that's how we're getting the closest version of the area, right? So that the number of rectangles is so many that it's basically the same as the area. Again, visually, that would be like instead of maybe only having, what do I got here, like 4 rectangles, if I made that much, much smaller until there were an infinite amount of rectangles, I would get closer and closer until I would be actually finding the area under that curve. So we're letting n go to infinity. Okay, for our x sub I, we're starting with our first term, and then we're adding that change in x, so whatever our delta x is. And then I is just going up by an integer because that's how much you're going up. Like, for example, if I wanted to start at 1 and then I wanted to go up by 1, my change in x would be 1, and my I would go up by 1. So then my next one would be 2 times 1, and so on and so forth. Okay. Okay, so let's actually try one. So in this first example, we've got our integral here, which remember is the sum of all of our values or our total area from 1 to 3 under this curve. So using our limit definition, well, first of all, we're going to let the number of rectangles, n, get infinitely large. And so we're going to have the sum, we want the sum of all of our rectangles from 1 to n of our function. Okay, so this is where we need to put in our function value. So let's do this. Let's go over to the side. Our function right now is x squared. So if I want to find my x sub I from the previous screen, because remember that's what's in here, then I need to go my first term, which my first term would be what I get when I plug in 1. So if I plug in 1, I get 1 squared or 1, plus the change in x. So I guess maybe let's find that change in x. So my delta x is going to be, well, let's see, we've got the difference between 3 and 1, which is 2, and it's divided by the number of rectangles, which is n. So, okay, there's my delta x. So I'm going to do plus 2 over n I. So let's put it all together. So we need to plug this value in to our function. So wherever you see an x, you're going to replace it with the xi. So instead of blank or x squared, I'm now going to have this. 1 plus 2 over ni squared. And then, of course, times my delta x, which is like your dx, and your change in x, as you know, is 2 over n. Remember, if you need to see that here, this is what we just did. So if you'll see, we changed it to limit notation as n goes to infinity from 1, I equals 1 to n. So it's, again, it's not f of this. It's literally like you're replacing the function with the x sub I, and the x sub I is this first term plus change in xi. Okay, and then again, you're attaching dx is the change in x, so you're attaching what the change in x would be. All right, let's try another one. Now this one has us going the other way, so we have to work backwards. So we have the sum written in limit notation. We want to go back and write it as an integral. Okay, so I think the first thing I would do is pay attention to what's on the outside, because what's on the outside should be your delta x. And so remember, delta x is found by doing b minus a, so your two integrals, all over n. So we know right now that the difference of our integral is going to be pi. So like in a minute when I go to write my integral, the difference between these two things should be a difference of pi. Okay, now what else can I find? Well, my first term should be here. Now I know that I can tell that my function, I hope you guys can too, my function is sine of x, because then everything's inside here. So my first term, it should be this first thing, which is pi over 4. So I can go over here and say, okay, the beginning of my integral must be pi over 4. The width of my integral The difference should be pi. So if I add pi to that, that gets me to 5 pi over 4 of my function. Remember, my function now is sine of x dx. So that's it. All right, same thing here. We want to know which one it's equal to. Here's a multiple choice example. So, okay, the first thing I'd probably do is get my delta x. My delta x is 2, changing 5 and 3 over n. All right, so then my different x values along the way would be, well, I'd start with my first term. Remember that my first term is the first thing I'm allowed to plug in, which is 3. So for my x sub I, I'm going to start with 3, and then my next value up will be whatever this change in x is, so 2 over n I. And remember, I is just going up by integers. Okay, so let's go over here and take a look. So I would have my limit as n goes to infinity. Everybody looks good. From 1 to n, okay. I start with 3. So far, so good. My change in x values should go up by the interval over n, which is 2 over n. So these guys are out. And then I should be multiplying by my dx, or change in x on the outside. So that's why that guy's out. So my answer would be D. All right, that's it. I told you it was going to be quick. Good luck. I'll see you in class for the problem sets.